Okay, so we are here in 3.2. And just as a review, we're going to talk about slide 1 really quick, or problem 1. And it says, use the table to verify that x cubed has a quadratic rate of change. So one of the things that you should be comfortable in is whenever we're looking at a particular function, in this case, it's x cubed. If you go 1 down from that x cubed now to x squared, that is going to be the function of your rate of change. Okay, that's going to be the function of your rate of change. Now, what does rate of change mean? It's just how your function is growing. So these numbers here, this very first set of numbers here, that is our rate of change. Now, when we're talking about the differences of the differences, I think some people are getting confused with these, like the function versus the rate of change. So I want to clarify this. Because what? Here, I'm going to have you guys fill this in. Because what, then this function I know is cubic. Because what, I know that this function is cubic. Because of what? Because of what? Because of what? I'm not really concerned. Pretend that you didn't know this function, like you didn't know it was x cubed here. How else would you know that it was a cubic? How else would you know that it was a cubic besides the x cubed up here? Pretend that that doesn't exist. Very good. So someone says, hey, Ms. Johnson, because of that third row of differences, I know it's a cubic. Someone says, so in case you don't know, what row of differences are we talking about? We're talking about this like super light pinky purpley color right here, right? So because of this color here, these 6 and 6, these numbers are the same, then I know it's a cubic. If the second row of differences were the same, then we'd know that this was x squared, because we know that if the first row of differences were all the same, then we'd know it was x to the first. Okay, so these are your differences. If your differences are the same in this row, or this row, then it's an x to the whatever function. Does that make sense? So here, if I give you a table like this, and that would be a really good question, and I'd say, okay, tell me what you know. And I just gave you a table like this. Tell me what you know. You should be able to tell me, well, the rate of change is 7, 9, 19, 37, 61, because those aren't the same. I know it's not linear. And then you did the differences again, 12, 18, 24, because those aren't the same. I know that this function is not quadratic. And because these are the same 6 and 6, that tells me that my function is cubic. And because my function is cubic, that means my rate of change is what? My rate of change is what? Because my rate of change is cubic, then it tells me that my rate of, I said it wrong. Because my function is cubic, it tells me my rate of change is what? Nope. So your rate of change is this. Because this is cubic, you step 1 down from that. So then this, the rate of change, if I wrote a function on this, so like, can you guys all pretend that I make another table? Actually, let's not pretend. Let's say I give you another table. In this table, I just really want this to be off to the side so that this is kind of like there. And I copy my differences here, right? So I go 7, 19, 37, 61. And I said, hey, and I don't know, this is 1, 2, 3, 4, and so on. And I said, hey, what function, like, what type of function is this? What type of function is this? And you guys would tell me what is this function? Yeah, this function is quadratic. How do you know it's quadratic, Ms. Johnson? Well, because if I copied these differences over here, which, can I copy? Am I allowed to copy things? Let me see if I can copy things. I think I can copy. Oh, but I don't want that. I just want this. Can I do that? Yeah. Look at me, so fancy. Okay, here we go. Boom, right? I already know So if I subtracted 19 minus 7, that's 12, 37 minus 19 is 18, and so on. I got those numbers here and this number here. So one of your classmates says, hey, Ms. Johnson, shouldn't that be quadratic? Yes. How do you know it's quadratic? How do you know this function is quadratic? What tells you that this is quadratic? This function over here. Let's call him G. Oh, are you not going to work now? Yeah, let's pretend this is G of X. How do you know G of X is quadratic? Yeah, exactly. Because the second set of differences, say this out loud. If you don't know this, say it out loud with me. Because the second set of differences is the same, it means my function is quadratic. So I'm just going to copy and paste because you guys are so fantastic at giving me the words. Since the second set of differences are the same, I don't have enough room. Where did it go? There you are. Sorry, I have too many things open. So here, because my second set of differences are the same. So this implies, hold on, let's write this down. This means in short term, this means it's a quadratic, right? So for those of you who don't know, this double arrow in mathematics means it means therefore kind of thing. So second set of differences are the same, therefore my function is quadratic. Good, so that's quadratic. Does that make sense? Someone asked about the third row of differences back here. They said, Ms. Johnson, is this linear? No, this is not linear. So let's count this out. This is cubic. Everyone said, Ms. Johnson, this is cubic, right? So this is cubic, right? This row, if we're counting down one, would be what called what? No, not linear. Yeah, it's quadratic. This row is called quadratic. What would this row be called? What would this next row be called? This one here. Okay, give me a second. Yeah, the next one would be called linear, right? The next one would be called linear. So can you guys practice like posting to the public, not just to me? Thank you for those of you who are posting to the public, not just to me. Okay, so Ms. Johnson, what does that mean? Like why is that important? Because the question asked you, how do you know that how do you know something is true? How do you know that the rate of change is quadratic? So you're doing it based on the fact that there's a couple of different ways, but one of the ways is looking at like how far the differences go between when they become constant. Okay, so this is linear, right? So this is linear. Okay, what comes after linear? What is this guy called? Anybody know this one? No, this is called constant. Okay, constant, no, not cubic. Constant means that it's not changing. If your parents constantly tell you yes, or parents constantly tell you no, no matter what you say, they're saying that thing. So Ms. Johnson is constantly telling you, stop telling yourself that you can't do this. Ms. Johnson is constantly telling you, make mistakes now so you don't make mistakes later, right? So constant means this, it's the same message over and over again, 6, and so on and so on. Here, okay, so again, do that same thing here. What is this function? You guys told me this function was what? You guys said it was quadratic. So, oops, I want to use a different color, sorry. Quadratic. Right? This one's called quadratic. What is this then called? If this is quadratic, the function is quadratic, what is the rate of change called? Yes, it's called linear. And what are those 6's called? What are the 6's called? Constant, very good. Okay, good. So more people are participating. Very good. Get your participation in here. How are you going to learn this stuff? How are you going to do well on a quiz that you've been silent on this whole time? Like, how am I supposed to go up to bat and hit a home run if I've never went up to bat? That's why it's called practice. It's okay to be wrong in practice, right? It's okay to be wrong in practice. All right. So that answers this question. Use a table to verify that x cubed has a quadratic rate of change. The other way to prove that it's a quadratic rate of change is this. If I took this and then I found the rule would have an x squared in it, right? So I don't know what the rule is. Let's see, 1 squared plus 6. 2 squared is 4 plus 6 is not 19. So then I'd have to play a little bit more in order to get this function. So the other way is to actually find the rule for this. Okay. Then it says graph x cubed, which you guys, for this one here, all I'm expecting you to do is go up here, graph x cubed. Is this what you thought x cubed would look like, right? Is this what you thought x cubed would look like? And you're like, huh, I didn't think so. Does anybody see anything here? Do you see this curve here? How it grows here, and then it's almost like flat here, right? And then it goes down, right? So that's what x cubed looks like. Not a big surprise because you guys could have used a calculator. This should kind of make sense. Questions that maybe pop up if I compared these two, and this is actually a question later on, which we'll get to, is comparing the domains and the ranges of those two, but we'll get to that later. It says, describe the features of x cubed, including intercepts, intervals of increase, decrease, domain, and range. Okay, so this is something that I do need to capture on our notes. So let's do that. Could you guys tell me some of the features of this graph? Oops, I'm gonna cancel this. I don't want this here. All right. So can you guys tell me some of the features of this graph according to what they're asking for? So here, I'll just put it right here. Okay, so describe some of the features, including intercepts, intervals of increase, decrease, domain, and range. Can you guys do that for me? What do you guys see? The intercept should be, intercept should be fairly, straightforward, very good. Okay, let me just grab a couple things. Okay, okay. So that should be fairly straightforward. You guys should all be comfortable with that. Yay, Miss Johnson. Okay, so let's snip things because then I could just prove that you guys are doing work and it's not just me. Okay, so intercepts at 0, 0, and it's interesting because both of those intercepts are at 0, 0. I'm trying to get to my snip, but it's like hidden behind my chat. That's what it does. Copy. So my intercept is at 0, 0. Very good. Done. Notice it's asked for intercepts, and both of the intercepts are at 0, 0, both the x and the y. Let's see. So yes, I agree with that. Someone else says, would the domain be all real numbers? I don't know. What do you guys think? Would the domain be all real numbers? What do you guys think? Domain be at all real numbers? So in case you're forgetting, Ms. Johnson, what is a domain? What is a whatever? The domain is look left from the left side to the right side. Do you see any values? Or actually it's asking, what do you see every value? And you're like, yeah, I kind of do, but Ms. Johnson, I don't know about here. When it goes off the screen, you can assume it continues in that fashion, right? So it's just going to continue all the way down. Same thing goes up. So for looking from left to right, are there any values that are excluded? And you're like, no. The range is looking from bottom to top. Do you see any values that are excluded? And you're like, yeah, I don't know what's happening out here. You can assume, again, it goes and continues in the same fashion. So for this one, the domain and the range are both all real numbers. And if you're trying to be fancy, remember that your real numbers is that fancy R with a double stick, right? Looks like that. Okay, intervals of increase and decrease we've kind of talked about before. So where is this function increasing? Where is this function increasing? No, when it's talking about an interval, whenever we say interval, you need a from to. From what to what? So where is the function going up? Up. Think up. Or is it increasing? From left to right. From the left to the right. So someone says, hey, Ms. Johnson, what about from 0 to infinity? The answer is yes, but even more. From left to right, is your roller coaster going up? And you're like, yes. And then it kind of pauses a little bit. It slows down its increase right here, and then it continues. So you can literally exactly, someone says, can I write it from negative infinity to infinity? The answer is yes. That is our interval of things. So I will write it like this. Negative infinity to infinity. And remember, we talked about these parentheses and brackets before. Infinity never gets a bracket because infinity is not an actual number. Okay, so very good. So this is an interval of increase. Okay, so let's remind ourselves really quickly. If I went over here and I turned off this and I turned on this, from left to right is your roller coaster going up. That's an increase. From left to right is your roller coaster going down. And you're like, it's doing both, Ms. Johnson, in different places. Very good. So when it's going up, notice I say the word when it's going up, that's an interval of increase. Chug, 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 right? When your roller coaster is going down from left to right, woo, right? That is a decrease, and that's an interval of decrease. So how would you say that, Ms. Johnson? Well, let's talk about increase first. Just ignore the decrease for a second. So when does the increase start for this function? When does the increase start for this function? Yeah, it's 0. It starts at 0. When does it stop increasing? When does it stop? Yeah, it never. So the never word in math is just infinity. So it would look like this, right? Now, if you wanted to put a bracket here, I'm not mad at you. You could put a parentheses. It doesn't really matter. I tend to use a parenthesis here because at 0, it's, yeah, well, that's a different conversation. I won't even bother you with that. So I would put it like this. See? And then parentheses. Notice that the infinity symbol always gets a parenthesis. He never, ever gets a bracket, ever. So this would be considered my interval of increase. Similarly, from negative infinity to 0 would be my interval of decrease. Okay, so you guys are comfortable with that. So I've answered all these questions. Don't be like intimidated by these questions. They're very conceptual, meaning you have to understand what they're asking, but they're very straightforward at the same time. So interval of increase or decrease, that's you looking from left to right on a roller coaster. Are you going up or down? And if you say both, you'd have to tell me when you are going up and when you are going down. In this case, from left to right, I'm going up, 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 up. So I started at negative infinity. I end at infinity because it doesn't look like it's ever going to come down. My intercepts are where it crashes into your X and your Y axes. And so for that 0, 0, domain and range. Domain is look left to right. Range is look from bottom to top. Okay, so now we do that. Now I can go relatively quickly. So it says use your knowledge of transformation and graph each of the following without using technology. Now, can you use technology to check your answers? Absolutely. But I want you to explain to me what these numbers actually do to this. So I already peeked at some of your answers. I was pretty impressed with some of your answers. So I'm going to take a look. Yep, you're anonymized. So a lot of you, let me see. Yeah. So a lot of you said different things like, oh, wait, not this one. This. Yes, this one. Okay. So some of you just graphed it and you didn't tell me what. So like, can you imagine it says use your knowledge of transformation, graph each of the following without using technology. Can you pretend you're the teacher right now? Everybody good? Would you give this person full credit? Would you give this person full credit? Everyone says what? Yes, no, maybe so. Yeah, I wouldn't give this person full credit. Why not? Because it says using your transformations, graph each of the following without technology, no words. So I have no idea what this person was thinking, so I can't give you full credit. So most of my questions are a lot more clear than this because I want you to be very clear. Ms. Johnson expects me to explain. So I would say something like this, using your knowledge of transformation, explain how this function is a transformation of another function of x cubed, right? And so you would then be forced to answer a question, maybe more a little along the lines of this. See, it says the intercept moves down 3 units. Very good. It's not just the intercept, the whole thing actually shifts down 3 units. Let's see, this person says, goes down as -3, isn't in parentheses. When it's in parentheses, it goes right and left. Very good. So this person's telling me, Ms. Johnson, I know what I'm doing. So if you wanted to make this a little bit more clear, it shifted the whole graph of x cubed down 3 units. It shifted the whole graph down 3 units, okay? Ms. Johnson, this person didn't graph it. That's all right, because in my eyes, I was really looking for this explanation, right? So Ms. Johnson, I don't have to graph it. If it says to graph it, you should graph it for sure. Let me see if is there any, oh, look, this person even points, this goes down 3, Ms. Johnson. Is this clear to you? Is this a clear picture, right? If you were the teacher, would you give this person full credit for this using your knowledge of transformations, graph each of the following? Would you give this person full credit? Everyone says, yeah, I give this person full credit because they're telling me what that number did to my function, right? That it told me. Let's see. Yeah, okay. So now you can use the knowledge that we used before in terms of functions and now see how we're applying it to this. This is very classic math to me. Classic math is like, I know what this guy looks like. Sorry. I know what this guy looks like. He looks like this, right? Oops, sorry, wrong one. This guy right here. This guy looks like this. And I know how to find this based on this, right? This is very classic math to me, right? Very classic. So again, Ms. Johnson, I know this goes down 3, and maybe you guys didn't write the explanations because it wasn't clear. That's fine, no worries. I would practice doing that because, you know, Ms. Johnson is a big, like, how did you know? What did you know? Okay, so let's look at this next slide. It says, using your knowledge of transformations, graph each of the following without using technology. And this one, this person says graph moves 3 units to the left. Perfect. Perfect. If they would have added the explanation of how they knew that or why they knew that or why it does that, that's like icing on the cake. That's not unnecessary unless I say, tell me why. So like that other person said, let me see, let's see this one. Yeah, like the other, this is the matching of the other person, right? This is because +3 is in parentheses, it goes to the right or to the left. It goes to the right or to the left. And then they didn't actually show me which way it goes. So, or why it goes that way. So this is just missing just a little bit. So let's find you a, let's see, this, it goes 3 to the right. This is pretty good. It goes 3 to the right. And then there's your explanation. Very good. So, yeah, these are pretty strong explanations. Just like you would ask your, you know, your little brothers and sisters. Yeah, right. Someone said, hey, Ms. Johnson, is this a good explanation? It goes to the left 3 because it's in parentheses affecting the X, and then X is backwards line. Absolutely. So this point that used to live right here at 0, 0 is now 1, 2, 3 to the left. And this point that used to be right here at 1, 1 is now 1, 2, 3 to the left. Okay. Yeah, that's great. So notice here, I didn't really have to teach you this. You're just kind of leaning on the idea of transformations. Technically something that I think you should have learned in integrated 1, but if you didn't, we reminded you here, right? So it says now use your knowledge for this. What does this 2 do to my function? Anybody know what 2 does to my function? Anybody know what this 2 does? Any guesses? I just did it, Angel. Yeah, it's no problem. It's technically called a vertical stretch. So let's compare both of these, right? So let's compare x cubed to 2x, that's not a 2, Miss Johnson, 2, that's not a 2, 2x to the third. Here's just so that we're all on the same place. Hey, can I ask a question? Does that cube affect the 2? Does that cube affect the 2? Does that cube affect the 2? No, it does not. Very good. Exponents can only see whatever is directly in front of them. Hi, Mr. Russell. He's in room 8, I believe. Okay, so that only affects that. Now look at the 2. Like if I zoom in here, look at this. Look at blue compared to red. Someone said it gets closer to the axes, and I don't like that answer necessarily, because it's not because it's moving closer to this axis. It's actually because the multiplier factor of it, it's being vertically stretched. So can you imagine that I'm holding the red function at the top up here and the bottom down here, and I'm stretching it this way, I'm pulling it down this way and up this way. Do you see how it stretches and it gets closer to the top? Closer, right? Okay. So that's why they call it a vertical stretch. So these coefficients that sit in front of our function, they bring the function up a little bit. So now if you were to look at, let's look at a particular number here. If you look at this particular number here, 1, 1, notice that he's stretched all the way up to 1, 2. Okay, and you're like, oh, Ms. Johnson, that's not much of a stretch. Okay, but let's look at, let's move over here. If we look at 2, 8, right? 2, 8 is right here. Where are you? There it is, 2, 8, right? So if you look at what the 2 is here, it's all the way up here at 16, right? So that 2 went from 8 all the way to 16. That 1 went all the way up to 2. So do you all see that this is a vertical stretch? You guys comfortable with that? Very good. Okay, so the correct mathematical term here is it's a vertical stretch. It's a vertical stretch. Okay. Then they are like, oh, what happens if we do all this to it? Now just take things one by one. So let's just take things one by one. What does this plus 2 do to my whole function? Yeah, it moves it up 2. Very good. Okay. Then what does that -1 do to my whole function? What does that -1 do to my function? Yeah, it moves it to the right 1. So if you're pretending here is my original point at 0, 0, pretend that's my original point at 0, 0. Okay, then it moves up 2, here it is. And then it moves right 1, here it is. Okay. So keep these things in mind. And then that negative, what does that negative do to my whole function? What does that negative do to my whole function? Yeah, it flips it or reflects it down. It reflects it down. Okay, it reflects it down. So like if you look at this, right? So if you look at x cubed, so x cubed versus negative, this is the power of technology, right? Like imagine me having to like plug this in one by one and I didn't give you a calculator, you'd be like, oh my gosh, Ms. Johnson, forever. So, but in the case that you did do that, you'd understand why it's flipping. Because here, when I plug in a positive number, say like the number 2, I cube it, I get 8. But here, when I plug in a positive number, I get 2, I get 8, and then I make the opposite, so it's -8, right? So it flips downward, like all the points that were up here now live down here. All the points that were down here now live up here. Okay, so then, so it flips the whole thing down. The thing that confuses students right now is there an order to our transformations? Is there an order to our transformations? Okay, and the answer is yes, kind of. As long as you make it make sense. Yeah, you move it to the right one because X lives in positive land. Very good. Very good. Okay, so is this where you expected it to go? The green function. Let me turn this guy off. Is that where you expected it to go? And you're like, yeah. So there's two ways to do this. And I prefer this way than the other way. The first thing that I do is I graph like the function with the flips and the reflections. So I graph negative x cubed like this, the blue guy. And then I shift him. I shift him up to right one. So if you notice, this point went up to right one, right? Up to right one, and that ended up here. Now, some people think if I shifted him up to right one and then I reflected him down, shouldn't he be here? That's why order kind of matters. So keep in mind that. Keep in mind order does matter. And then use your calculator to check your guess. Okay, so we said that it moves up to right one and then it flips. So, and then it flips technically means that it flips over this line here and then it ends up down here. But that's not what I think you meant. I think you meant instead of this shape here from bottom to top, it's going from top to bottom through this point. Okay, so be very aware that there is an order to get to that point there, especially with multiplying by a negative, because it does matter. The way I would check it, Ms. Johnson, what if you want us to check it and verify it? Well, I would just start plugging in numbers, right? Like, so if I plug in the number 1, I should get this number right here. That was my guess, right? If I plug in 1, I should get this number here, right? So let me plug in 1. So 1 minus 1 is 0. 0 cubed is 0. Negative of 0 is 0 plus 2. Boom, it's at 2. Let me just check one more point just to make sure, Ms. Johnson. Sure, my other favorite number to plug in is 0. So 0 minus 1 is negative 1. Negative 1 cubed is negative 1 times negative 1 is positive 1 plus 2 is 3. So was my next point going to be right here? And I said, yeah, because you guys told me to go from top to bottom, not bottom to top. So those are the verifications that I need you to kind of go through to make sure that you're understanding these shifts. Okay, let me check something real quick. Okay, so yes, we did check our graph. So figure out where you need to improve on in your graph. Okay, I'm going to pause right here for a video.